right, we're just jumping back a little bit. We're going to continue some things with continuity and differentiability now that we've learned some shortcuts to find the derivative. It's going to make some of this stuff a little easier than if we were to do it using the limit definitions. So example 1 in practice problems 1 through 2 have the same directions, and it is to find the value of k that makes the function continuous everywhere if possible. So just a quick review about continuity. For a function to be continuous at a point, the limit as x approaches that point from the left of the function must equal the limit as x approaches that point from the right of f of x. So those limits have to be equal, and that also has to equal f of a. So that means f of a must be defined. So if there is not a value for the function at x equals a, then the function cannot be continuous. All right, so let's look at this first example. We have a piecewise function, so these are all going to be piecewise functions, and we want to find the value of k that will make the function continuous if possible. So I'm just going to write my notation using the limit. So the limit as x approaches 1. So 1 is the value that is questionable, because that's where we change pieces. So if we are approaching x from the left, this one is in a different order than they usually are. So from the left, we're going to use the second function, because that's where the x's are less than 1. And that needs to equal the limit as x approaches 1 from the right, which will be the first function. Or the first piece, I should say. All right, and so what we'll do is just go ahead and plug 1 into both of those x's. All right, so I'm going to go ahead and add the 1. So k is going to be equal to 1/2 minus 2 plus 1. So 1/2 minus 1 is going to be negative 1/2. So as long as k is negative 1/2, those two pieces are going to touch each other. And let's check one more thing. For the function to be continuous, there must be a value when x is equal to 1, and there is. Because I have that or equal to, when I put 1 in, I already know that I'm going to get, we can figure it out. But anyway, as long as there's no or equal to there, the two limits match each other, then we're good. That's going to be our k. Okay, so use the same process to do practice 1 and 2. So that's part of your assignment. All right, and then example 2 and practice 3 and 4 have the same directions, which is to find the value of a and b that make the function differentiable everywhere if possible. So for a function to be differentiable, the function must be continuous. And we just wrote down what we needed for continuous. So I'm just going to draw an arrow. Not a very good arrow. So all of that pink stuff has to happen if the function is differentiable at that point. And extra stuff. The other stuff that has to happen is that the limit as x approaches a from the left of f prime of x equals the limit as x approaches a from the right of f prime of x. So their slopes match in the left and right also. So it's going to be a new part for us. All right, so the first part we're going to do just like what we just finished doing on example 1. So we want we want the limit as x approaches x approaches 1, because 1 is the value where things happen here. From the left side is going to be the 3x minus x. That needs to equal the limit as x approaches 1 from the right of the other piece. All right, so then we'll put 1 in for our x's. So that's going to give you 2 is equal to a plus b. All right, so when we finished that on example 1, we knew what k was. We can't solve that equation for a or b because there's 2 things we don't know, 2 unknowns. But I'd be willing to bet once we do the second part of determining whether a function is continuous, we'll be able to finish it up. So what I'm going to do next is I'm going to find f prime of x. So to do that, we're just going to find the derivative of each piece. So if I want to find the derivative of the first piece, 3 minus x, we're going to use the power rule. So the derivative of 3 is 0. The derivative of negative x is negative 1. And we use that derivative for x's that are less than 1. Right, and I'm going to use the power rule on the second piece as well. So I'm going to multiply by my power and then subtract 1 away from the power. Same thing on the second term, bx. The derivative of bx is just going to be b. All right, so I'm going to find the limit as x approaches 1 from the left of f prime. So that's just going to be that first piece, which is negative 1. That needs to equal the limit as x approaches 1 from the right of the second piece. Okay. And anytime you have the limit of a constant, our constant is negative 1, is just equal to that constant. For the second piece, I'm going to plug 1 in for x. Okay, so I get another equation that has the same 2 variables. That is called a system of equations. And it may have been a while since we've solved system of equations. But what we'll do is we'll take them, we're going to line up the a's and the b's. So we're going to solve this by elimination. So I'm going to just kind of rearrange it a little bit. So I have a plus b equals 2, which is the 1 on the left. Underneath, I'm going to put 2a plus b equals negative 1. All right, so then what I'm going to do to solve this is I'm going to eliminate b by subtracting these subtracting these equations. All right, so I have a minus 2a is negative a. B minus b is eliminated, that's 0. And then 2 minus negative 1, that's minus negative 1 is plus positive 1. So that means that a is negative 3. And once we know what one of the variables equals, finding the other one is really easy. We'll just take negative 3 and put it in for a there. So b is equal to 5. Okay. All right, so what you guys will need to do is do those 4 practice problems, please.